Hello students. Topic 8 is another application. It's on mixing solutions. There are 4 tasks in this lecture. First task, a 40-gallon tank initially contains 10 gallons of pure water. A salt water solution at a concentration of 20 grams per gallon is pumped into the tank at the constant rate of 4 gallons per minute. At the same rate, the salt water solution is pumped out. Find the following. All right, the first thing I'm going to notice to do is I'm going to draw a little picture of the situation and try to understand what's going on with the salt. So I'm going to draw a little container here. Oops, let's do this. A little container that represents a container, or a little rectangle that represents a container. This is a 40-gallon container, although it holds 10 gallons of water. So let's get some water in here. 10 gallons of pure water. And into this container we have a salt water solution at a certain concentration being pumped in. So going into the container, we have salt water is being pumped in at 20 gallons, or 20 grams per gallon, and 4 gallons per minute. Water is leaving, it said, at the same rate. So we're losing 4 gallons per minute. Now what this suggests is that the volume, the 10 gallons of water that was in here initially, will not change because water is flowing in, a solution anyway, is flowing in at the same rate that it's leaving. Now let's assume, so we have salt water entering a pure water solution. Let's assume that once the salt water enters, it's instantly mixed and then it leaves. So we expect to see the salt water concentration rise over time as this process continues. Now we want to create a function that represents, looking at item number 1 here, find a model of the amount of salt in the tank as a function of time. We'll do this by hand. Let's use x to represent this function of time. So this is the amount of salt in grams in the tank as a function of time. Now we're going to create a differential equation from this scenario. dx dt is the rate of change, and its units are x is measured in grams and t is measured in minutes, we'll say, because that's the unit that's provided for these rates. So we want this to be a grams per minute. And we can find the rate of change in the amount of salt by doing the rate of change in minus the rate out in grams per minute. This is an important realization to know what the units are for this derivative. The rate of change in x with respect to t, and x is the amount of salt in grams in the tank. Okay, so we just have to analyze the rate at which salt is entering the tank and the rate at which it's leaving, and construct this differential equation doing rate in minus rate out, and we can then solve that equation and figure out what x is. So dx dt is simply x prime, so I'll go back to x prime. X is our dependent variable, t is our independent variable. The rate in is, we have 20 grams per gallon times 4 gallons per minute. So this tells me how many grams per minute. Remember, we're after grams per minute here for the rate in. And if you multiply them, we'll say 20 grams per gallon times 4 gallons per minute. This gives us 80 grams per minute entering the tank. Now the rate out is a bit trickier, because once the solution enters the tank, then there's an unknown amount of salt in here in the tank. So we have to figure out, let me go ahead and return to this one and put our values with units here just so we can see this construction. We're going to mimic this construction for the way out. So there's our rate in minus. Now the question is how many grams per gallon there are. Well, at any moment in time, we're using X to represent how much salt is in here. So there's X grams of salt in the tank at time T. And there's 10 gallons in the tank. The volume is 10 gallons. So our rate is going to be X grams divided by the 10 gallons. And that's how we mimic this fraction here, or this rate right here. But then the water is leaving at the same gallons per minute rate. That GL is GAL, gallons per minute. And so we're leaving at 4 gallons per minute. Okay, now if you keep track of all the units, then this will be X prime is equal to 80 grams per minute minus 4x over 10, which is 2x fifths grams per minute. And just like that, we have constructed the differential equation that we need to solve. This particular differential equation is separable. Let's go back to dx dt. I'm going to factor out the negative 2/5. That leaves x minus, and factor out 2/5 from 80. That's going to give us a 200. And just double check, verify that this works. Negative 2/5 times negative 200 is 400/5. That's 80. So that does work out. Our factoring is done correctly. Then separate the variables. Okay. Oops, dx on this side, dt on this side. Integrate both sides. Natural log of x minus 200 is equal to negative 2/5 of t plus a constant. Exponentiate and then add the 200 to the other side. I'm going to skip some of these steps because we've done this a bunch of times. X is equal to some unknown constant times e to the negative 2/5 of t and then plus 200. This is our general solution. I'm going to go ahead and graph it in Desmos. Y equals, Desmos doesn't like x of t as entering as a function. I've noticed it doesn't produce a graph that is as expected, at least as I expect. So I'm going to say y equals let's do capital A, just capital A, times e raised to the negative 2/5 of, we can use t still for the independent variable. I'll go ahead and use t, and then plus 200. I'm going to add a slider for capital A. And then for the slider, let's let it range from negative 200 to 400. And then hit play and see what happens here. Currently I see no image. Oh, now I do. So let's change our scale. I'm going to change our vertical scale until I can get, oh, here we go. Now I'm seeing all the different possible solutions. Notice all of them follow 200 as a limit. We'll talk about that in a moment, why that's the case. Now we want to find our particular solution. And we know that at time 0, okay, so at time 0, how much salt is in the tank? We need to have an x prime of 0 condition. And the key to knowing this is right here, 10 gallons of pure water, suggesting that initially there's no salt. So we know that x of 0 is equal to 0. I'm debating where I'm going to put this work. Yeah, let's put it back up here. X of 0 is 0. So we know that 0 is equal to a times e to the 0, which is just 1, plus 200. So that gives us a is negative 200. And so we finally get our model. X as a function of time is equal to Let me move. I'm going to move everything. Give myself a little bit more space here. Move all of this over. Here we go. X of t is negative 200. That's what our A is. Times e to the negative 2/5 of t, and then plus 200. And this answers question part 1. Now, let's go back to our model over here and let A actually be negative 200. And so here's the model of how much salt is in this tank as time elapses. Notice it's approaching 200 over time. The amount of, now question 2 I'm looking at next. The amount of salts in the tank after 5 minutes. Use technology. So I'm going to make a vertical line, x equals 5, because you write, I should be saying t equals 5, but to make a vertical line in Desmos, you have to write x equals. So even though technically my independent axis is t, and my horizontal axis is t, and my vertical axis is x, because I'm using x to represent how much we're using x to represent how much salt there is in the tank. X is our dependent variable, but Desmos really doesn't like when you treat x as the vertical variable. That's why I wrote y equals when I did the grid graph, and why I have to say x equals to make a vertical line. But anyway, so this is really at time 5, not x equals 5, but time equals 5. There we go. Oops, come back please. Thank you. At time 5, we can see that there's 172.9 roughly grams of salt in the tank. So this would look like the following. X of 5 is approximately equal to 172.9 grams of salt. Okay, I'm just going to erase that number 1. This answers question 2. Or I'll do it in red. There's question 1, here's question 2, and next question. Find the time for the salt in the tank to reach 150 grams. All right, so the vertical axis is how many grams we are, so we want to do a horizontal line. Okay. And that's typed in by y equals 150. Find that time right there, and we can see that the time is about 3.466 minutes, we'll say. Or 3.47 rounded. Unit is in minutes. And this answers question 3. And 4 is the eventual amount of salt in the tank. And so that means what is the limit as t goes to infinity? And notice we were asked to do this by hand. And I'm going to copy this formula, bring it down here, paste. And as t goes to infinity, we're going to get an e to the negative infinity here. This part here approaches 0 as t approaches infinity, which means that x approaches this 200 right here. And that is the answer to our 4th question. Now, why 200 grams? Well, the concentration of the salt is 20 grams per gallon. That's the concentration being pumped into this. Eventually, the entire tank will approach that same concentration, 20 grams per gallon. And since the volume is being fixed at 10 gallons, if we're pumping in water, saltwater solution at 20 grams per gallon, eventually this is going to approach that same concentration, 20 grams per gallon, and there's 10 gallons, so that means there should be 200 grams of salt in here eventually. And it's going to get to the point where effectively the concentration that's leaving is equal to the concentration that's entering. Another way to figure out this 200 grams is to set the x prime equal to 0. Take this line right here. If we expect the concentration to cease changing, then x prime will be 0. No more change in salt. If you set x prime equal to 0 and solve this for x, you will find 200 is the solution. So 200 is the value. Once there is 200 grams of salt in this tank, it will no longer change. It'll stay 200. Okay, let's go to the next task. Repeat the last scenario, but assume the tank initially held 250 grams. Find the following. Notice it's all the exact same questions. The only difference is our initial condition, so we can actually leverage quite a bit of work that was done up here. In fact, I can go right to this point right here. Everything up to that point will the same work. But now we get to the point where initially there was 250 grams of salt. So we just have a different initial condition. X at time 0 is 250 grams. So plug in 250 for X. At the same time, you change E to 0, T to 0. So this part here will just become 1 again. So you have A plus 200, and then subtract the 200, and we get A is 50. So our model is x of t is equal to 50 times e to the negative 2/5 of t plus 200. Okay, going over here to Desmos, let's change a to 50 instead. There we go. Notice our initial condition, 0, 250, so there's 250 grams of salt in the 10 gallons initially. And over time, we have still approaching 200. Oh, and the other questions were at 5 minutes into this. You can see that 5 minutes in, we have 206.8, we'll say. So x of 5 is about 206.8 grams of salt. Make sure I type that in right. 206.8 approximately, okay. This answers question 2. This was the answer to question 1. Question 3 is, at what time do we expect there to be 150 grams in this tank? And we would say never, right? This started with more than 250 grams, and it slowly dilutes, if you will, down to 200 grams total, which is a concentration of 20 grams per gallon. So there will never be a moment where there's only 150 grams. So for question 3, at no time, we'll say, will x equal 150 grams. And that's how we would answer that third question. And then for the eventual amount of salt, we do the exact same analysis on this function. We still notice that this part here will approach 0 as t approaches infinity. That's going to zero out the entire first term, and so x itself will approach 200 grams still of salt. And here we've answered the same 4 questions, but with a different initial condition. Okay, let's go to the next task. Repeat the previous scenario, but assume the solution leaves the tank at 5 gallons per minute. Find the following. Okay, so we now have the water leaving at a different rate, or the solution leaving at a different rate. We're repeating the previous scenario, so we're going to assume that initially we had 250 grams. But okay, so I'm going to copy some of this information from the very original and see what it is we need to edit. I'm going to copy that, bring it down here. All right, so in the previous scenario, we still had the water flowing in at 20 grams per gallon and 4 gallons per minute, the solution flowing in. We began with 10 gallons, and water is now pumping out, though, at 5 gallons. So this is one change. We're making this change right here. This is 5 gallons per minute that their solution is being pumped out. And the other that we're borrowing from last time was that the initial condition, x of 0, is, again, 250 grams. Okay, look a little bit better. There we go. 250 grams is our x sub 0. So I think we've copied the past problem, which is really a copy of the original. We're keeping this initial value, 250 grams, and we are now making one more tweak. Water's leaving at 5 gallons per minute. Okay, so I think we're at our scenario. Let's see what we need to do about this to tweak it. The first part, the rate in, that's not changing, but the rate out, we do have some changes here. First of all, we don't have 10 gallons of solution in there constantly because we're going to be losing some. We'll talk about that in a moment. And we're losing at the rate of 5 gallons per minute. Now, because this rate here and this rate here are different, our volume is not going to remain constant. That's an important change here. In fact, the volume will lose 1 gallon per minute. That's because solution is being pumped in at 4 gallons per minute, but we're losing 5. So every minute the net change is we've lost 1 gallon every minute. And so we need a volume function. Volume is not constant, it's a function of time. We started at 10, but once the process got started, we're losing 1 gallon every minute. And if t is measured in minutes, then we just have to say minus t. Right, so whatever t is, so if 3 minutes have gone by, then we've lost 3 gallons, and our new volume would be 10 minus 3, or 7. So that's important. 10 gallons is no longer a constant. Our volume is now a function of time. It's 10 minus t. And therefore, our concentration will be x grams of salts per 10 minus t gallons of solution. So we actually get a 10 minus t gallons right here in that part of our denominator. Whereas in the previous tasks, this part was it was x grams per constant 10 gallons because the flow rates of 4 and 4 matched. Okay, so this becomes our differential equation. And let me move some of these things around just to make sure I have space. Without all these units here, it would look like x prime is equal to 80 grams per minute minus 5x over 10 minus t grams per minute. This is no longer a separable differential equation, but it is linear. So I could use the integrating factor technique. And that technique is our dependent variable is x, so we have x prime, so get that isolated on one side, which it already is, then move over the x term to that side with it. So this here I'm going to add to that side, and we get x prime plus 5 over 10 minus t times x is equal to 80. So this is our basic structure for setting up an integrating factor technique. And then this function of t that's in front of the x, this is our p of t. And the integrating factor that we want to create will always be e raised to the antiderivative of that p of t function. So in this case here, it's going to be e raised to the integral of 5 over 10 minus t dt. So this integral, we need to do a u substitution. Let u be 10 minus t, then du will be negative t dt. So there's going to be a negative as a consequence of the chain rule. We'll have a negative 5 over u du. That's a negative 5 natural log of u. And so we get negative 5, or e raised to the negative 5 natural log of u, and u is 10 minus t. All right, I know I did a lot there without showing the work. Don't worry about the plus c right here. We don't need that when we're doing an integrating factor. But this is review. I expect you to be able to do these basic antiderivatives at this point without error. The next idea, to simplify this negative 5 property of exponents can be brought up as a power, and then this e and natural log can cancel each other. So we get just this raised to the minus 5. And also I don't need the absolute values on our integrating factor any longer. So we're going to get 10 minus t to the negative 5 is the integrating factor. This will work. Let me move all this over slightly. Okay, the next thing we do is we multiply both sides of the differential equation by the integrating factor. So I'm going to do this. I'm going to do this. I'm going to copy our differential equation. Don't need that orange. And we are going to multiply both sides of it by the integrating factor. And distribute and see what happens. Okay, I'm going to move my work up here. And so I'm going to distribute. We're going to have x prime times 10 minus t to the negative 5 to get started. So 10 minus t to the negative 5 times x prime plus, this is 5 times 10 minus t to the negative 1. So when I multiply it by this, we're going to combine the exponents. It'll be now negative 6. So we're going to have a plus 5 times 10 minus t to the negative 6 times x. And then over here we just have an 80 times 10 minus t to the negative 5. Move that over slightly. So we get equals 80 times 10 minus t to the negative 5. Okay, so here's the result after I multiply by the integrating factor. Now, because of this process, this left side will always be the result of a product rule, and that product rule will be the derivative of the dependent variable, which is x in this case, times the integrating factor. And the other side stays the same. Oops, and I forgot my closing set of parentheses for this derivative. I'll make it brackets instead of parentheses. Let's just verify that this product rule does in fact, if I do the product rule on this statement, I will in fact get this statement. Oh, and I should also say this is not a derivative with respect to x, this is a derivative with respect to t. That's very important. So when I differentiate this product, we do the derivative of the first, and the derivative of x with respect to t is not 1, it's x prime. Because x is our dependent variable and t is our independent variable. So the derivative of x is x prime, it's right there, times the second, right there, check, plus the first, x, which is right there, check, times the derivative of the second. If we differentiate this, the negative 5 would drop down to the front, 10 minus t would be repeated, new power would drop to negative 6, and the chain rule would output a negative 1. And this negative 5 and negative 1, those would become positive 5, and so sure enough, here is our derivative of the integrating factor. So this does work. This product rule, doing the product rule on this does produce this statement right here. So we are safe moving forward. Now I'm going to integrate both sides. So when I integrate the left side, integrate a derivative, they just cancel. So you get x times 10 minus t to the negative 5. And the other side we still need to integrate, so I'll do that in my next line. 10 minus t to the negative 5 dt. So we're integrating this. And we need to do a u substitution. Let u be 10 minus t. And when let u is 10 minus t, then we have negative 1, or du is negative dt, so we're going to have a negative as a consequence of the chain rule. This will be integrating u to the minus 5. So we're going to increase that power to negative 4. Divide the 80 by negative 4, but then also the negative consequence of the chain rule. So this should just wind up being a 20 10 minus t to the negative 4 plus c. Let's just verify that real fast. I'm going to find the derivative of this and see if we do get this integrand. All right, so the negative 4 would multiply to the 20 and give a negative 80. Then this would repeat, power would drop to negative 5. And then the chain rule, the derivative of this would be a negative 1, and that would turn to the negative 80 back to a positive 80. So sure enough, when you differentiate this, you do get this integrand. Check. And now we just got to multiply both sides to get x by itself. I'm going to multiply both sides by, let's write it this way, 10 minus t to the positive 5. That'll isolate the x for me. So now we get our function x equals And when I multiply 10 minus t to the 5 times 10 minus t to the negative 4, the exponents add, giving just a 10 minus t. So we have a 20 times 10 minus t plus a c times 10 minus t to the 5th. Okay, and here is our explicit general solution. Now we're going to use the initial condition that we have x of 0 equals 250 grams. So we do 250 for x, because x tells us how much salt there is. At the same time, t is 0. So change all the t's to 0. We get a 200 for the first part, plus a c times 10 to the 5th. 10 to the 5th is 100,000. Now solving for c, I'm going to subtract the 200, so we get 50 on one side, and then divide by the 100,000. So c is equal to 50 over 100,000. Let's see if we can simplify this a bit. That's going to be 5 over 10,000. And we can simplify that even further, 1 over 2,000. So now I'm ready to write my explicit answer with the correct c. So I'm going to copy and paste and put the correct c in place. It's 1 over 2,000, so I'll just put this term here over 2,000, like that. And we have an explicit answer, which is a model of the amount of salt in the tank as a function of time. So we've answered question 1. Finally got to an answer for question 1. And we're going to use technology next for the question 2, which is find the amount of salt in the tank after 5 minutes. Use technology. So let's go ahead and go to open a Desmos. I think let me close that stuff, get Desmos back open. And I'm going to say y equals, and I'll make my function using y and x as the dependent and independent, even though over here they're x and t. Desmos does not like it when you try to use x as a dependent variable, which is unfortunate, but that's just the way it's programmed. So I'm going to say y equals and use x as my independent variable. So we have 20 times 10 minus x plus, and then we had 10 minus x, and all of that had to be raised to the 5th, and then all of that was divided by 2,000. Let's make sure this looks right. 10 minus x to the 5th over 2,000. Okay. I think I typed it in good. Let's change our scale so we can see what's happening here. All right, notice what is going on. According to our model, the amount of salt is decreasing with time, even though we're pumping a salt solution into this tank. Well, the problem is that the tank is losing more solution than it's gaining every minute. So we are steadily losing volume. Let's go back to our volume expression right here. Right, we lose 1 gallon every minute. So after 10 minutes, our tank will be empty. As soon as water flows in, it flows back out. There'll be no more water contained in the tank at the 10-minute mark. And so the obvious answer should be that at the 10-minute mark, there is no salt in the tank. So that was something that we probably should have observed to answer question 3 from the very start. Because if we're losing volume, then after 10 minutes, there can't be any salt left in the tank. The salt solution, as soon as it enters, it exits at this point. And so the answer to question 3 is the eventual amount of salt in the tank is 0. Let's go ahead and answer that right now. At the 10-minute mark, x of 10 will be 0 grams. So that answers question 3. And now question 2. What's the amount of salt in the tank after 5 minutes? So after 5 minutes, I'm going to do a vertical line, x equals 5. And then find that point of intersection. And that's going to reveal how much salt we expect to see in the tank at the 5-minute mark. 101.6 approximately. x of 5 is approximately 101.6 grams. And there is our answer for the second question. Okay, now let's do the last one. Repeat the first scenario, but assume the solution leaves the tank at 2 gallons per minute. Find the amount of salt in the tank at the precise moment the tank fills up. So I'm going to copy a lot of this initial information. Let's copy all this. Okay, so this time we have water leaving only at 2 gallons per minute. So there's going to be a change in volume here, non-constant volume again. The volume changes by, if you gain 4 gallons but lose 2, so you're going to ultimately gain 2 gallons per minute. So in other words, our volume as a function of time would be 10 gallons is what we started with, plus 2t, where t is measured in minutes. 2 gallons per minute times t minutes will give us the extra gallons. So again, we do not have a constant volume right here. We have a volume that is given by 10 plus 2t. All right, so we need to make some changes to this part again of our rate out differential equation. The rate in is the same, but the rate out is going to be, we still have x grams in here at any moment. That's what x stands for, is how many grams of salt are in the container. But it's no longer 10 gallons that are in the container. It's 10 plus 2t gallons. So we have x grams per 10 plus 2t gallons. And then times, and it's not 2 gallons per minute that we're losing it at the rate of 2 gallons per minute. Okay, so our differential equation becomes x prime is equal to 80 grams per minute minus 2x over 10 plus 2t grams per minute. And this one can be simplified a little bit. So we have 80 minus x over 5 plus t. I just simplified that fraction. Again, this is not a separable differential equation, but it is linear, so we'll use an integrating factor. We have x prime plus, I got to move this term over to the left side, so plus a 1 over t plus 5, I'll write it that way, times an x is equal to 80. Right. This 1 plus 1 over t plus 5 is our p of t, and our integrating factor will be e raised to the antiderivative of that. So that gives us e to the integral of 1 over t plus 5 dt. The integral of 1 over t plus 5 just winds up being a nice clean natural log of t plus 5. We can cancel the e natural log and just go with the positive version of this. T plus 5 will be an acceptable integrating factor. So to multiply both sides by t plus 5. So we're going to get just a 1 times x here. Okay, and here's our result. T plus 5 times x prime plus x equals 80 times t plus 5. Once again, I recognize that the left side is the result of a product rule. And let me move this over slightly a little bit more. And that product rule is the derivative of the integrating factor, which is t plus 5, times the dependent variable, which is x. Let me actually write this down here. One last line down here. Okay. Didn't mean to copy those. So we get to this line here. And again, after you apply the reverse product rule, it's always a good idea to double check it, right? How do you differentiate this product with respect to t? We do the derivative of one factor, so the x prime, check, times the other factor, check, plus the second factor, x, check, times the derivative of the first factor, which is 1, check. Now I can integrate both sides. So we're going to get t plus 5 times x is equal to the integral of 80 times t plus 5 dt. Okay, now you can integrate this right side as it is. You could let u be t plus 5, or you could distribute the 80 first. I'm going to choose to distribute the 80 first before I actually do the integral. So we're really integrating 80t plus 400 dt. Okay, so go ahead and now integrate that right side of our equation. We get 40t squared plus 400t plus a constant. And the last step, of course, is to get x isolated. So x as a function of t is equal to, and we get all of this repeated, and then divided by this t plus 5. Now we're repeating the first scenario, and in the first scenario, the initial concentration was pure water. So the amount of salt at time 0 was also 0. So we had x of 0 is equal to 0 again. So plug in 0 for the function. At the same time, we change all the t's to 0. So I get c up top and 5 on the bottom. This tells me that c itself has to be 0. Let's write that here to the side. So c must be 0, which means my function of t, copy and paste, is simply this function, no constant. Okay, now we were asked to find, in this task, find the amount of salt in the tank at the precise moment the tank fills up. So this is finally the first question where the capacity of the tank became important. And what was that capacity of the tank? We'll have to go back to the first scenario and take a look. It was a 40-gallon tank. So the capacity was 40 gallons. And we had only 10 gallons initially, but it's gaining 2 gallons per minute. So we want to really figure out is what the volume will be. How many minutes will it take to fill up this container? Well, there's a discrepancy, an initial discrepancy of 30 gallons, right? So we had 10 gallons to begin with, and we had 30 gallons to go to fill it up. And we're gaining 2 gallons every minute. So it's going to take 15 minutes. Right, the volume, 15 minutes in, will equal the 40 gallons, which is our capacity. Right, that's another way to do this, of course, would have been just to take this expression here, change volume to 40, and solve for t. Right, subtract the 10. So it's saying, okay, you're gaining 2 gallons per minute, and you want to gain 30 gallons. Divide by 2, you get, it takes 15 minutes to get the volume up to 40. Right. So the volume at time 15 will be 40 gallons. So we want to find the amount of salt at that same amount of time. So let's go to Desmos. Let's hide this image. We're going to go y equals, and our function was 40t. We can use x if it's not too confusing. We're using x for t and y for x. I know that sounds confusing, and it kind of is, but let's just use x instead of t because x is right here on my keyboard. Plus 400 x, and then I got to put this numerator in parentheses, and then divide, and everything is divided by x plus 5. Okay, so here is our model for how much salt is in, let's change this, how much salt is in the tank as a function of time. Now, this model does not take into account that the capacity was 40 gallons. we had to determine that at time 15 is where we kind of want to stop this, because then the tank will start to overflow after 15 minutes. So we really just need to, you could crop it here by doing the crop notation, which is we want to graph this for x is between 0 and 15. That's all that matters. Or you could leave it uncropped and just realize that mentally we want to crop this thing. But let's find out what, let me call this, let me graph now y equals 15, or x equals 15, so we can see where these intersect. There we go. So this tells us that after 15 minutes of this process, as soon as the tank fills up, that there will be 750 grams of salt in this tank. And this answers really the only question that was asked. Find the amount of salt in the tank at the precise moment the tank fills up. But of course, finding the particular solution was a key component. And that wraps up this lecture on using differential equations to model scenarios where we're mixing solutions.